Okay, let's get started. Today, Suwan is going to introduce us this defense thing. So let's get started.
I'm Suwan, and 이거 꺼주세요.
I'm also one, and this is the presentation I used in my master thesis defense. So it's about adaptive maximum entropy, regularization for connectionist temporal classification. So this will be the content of my presentation. First, I will explain my task along with the connectionist temporal classification, that's known as CTC, and its related works. And then I will introduce my adaptive maximum entropy regularization. So first, I will introduce the task and the related works. This section will cover from sequence to sequence learning, connectionist temporal classification, and its related works. Sequence to sequence learning takes a sequence from one domain as an input and outputs a corresponding sequence from the another domain. Input and output sequence have variable lengths, and the examples are mirrored machine text translation, which inputs text and outputs text, speech recognition, which inputs audio sequence to output and text sequence, and image captioning. One challenge is that input and output lengths are generally not the same, and thus hard to find the element-wise synchrony between each element of input and output. So for the specific case, monotonic sequence to sequence learning considers the cases where order alignment exists. In other words, the temporal order of input sequence and elements is preserved in the output sequence. Speech recognition and text recognition, which are our main tests, are the example of monotonic sequence to sequence learning. For example, it is possible to find the alignment between each text token and the speech time frame as shown in this figure. Text image also have such column-wise alignment with, for example, in this image TECHS along the horizontal axis. So this alignment is a very important condition and also information for model training. However, the challenge is that such explicit alignment information is hard to acquire in general, which limits the data set that can be used. Connectionist temporal classification, as known as CTC, is a powerful tool for sequence-to-sequence learning, which used without such explicit alignment information. So CTC is a type of maximum likelihood estimation, which is the goal is to maximize the conditional likelihood of the output sequence given the input sequence. For this conditional likelihood, CTC considers every possible alignment called paths between input and output sequence. For example, in this figure, CTC considers every possible alignment of the element of the dog with the audio time frames to get the total likelihood. So the CTC likelihood is the sum of the every possible feasible paths and uses the dynamic programming for efficient computation of all possible paths. 줌에서 나가죠. One important key in CTC is the blank symbol, which is an additional label to distinguish the consecutive identical symbol in target sequence. For example, in hello, there's two L's, and CTC inserts the blank between the first and second L, like in here, which enables the to decode them separately. In practical implementation, like in this example, CTC inserts the blank between each symbol, including the head and the tails of the target sequence, to compute the total likelihood. However, since blank symbol takes up half of the input sequence, CTC estimates higher posterior for blank symbol during the aggregation of the likelihoods. And because this posterior is backpropagated during the training, model trained with such posterior thus favors a blank symbol. As a result, CTC trained model tends to predict blanks only in the initial stage, as in this fourth stage in this figure. However, since the blank-only sequence is not the core sequence, it is penalized by the CTC loss, and therefore CTC tries to insert the single frame of the non-blank symbol of the label sequence between those blanks, like in this last stage of the figure. So resulting in sharp. So this results the sharp narrow spikes in the non-blank prediction, where non-blanks are generally predicted for one or few time steps. Moreover, CTC error signal is proportional to the path likelihood. In other words, once the model finds a very likely path, CTC loss tends to concentrate on that single path, and that path is the peaky path that is mentioned earlier, and the CTC trained model results in peaky predictions. This is called the peaky behavior of CTC, and such is-aligned peaky prediction can be seen as a type of overconfidence. There were several previous works to mitigate such behavior, and one previous work tried to mitigate this peaky distribution using the maximum entropy regularization. So ENCTC diagnosed the cause of the peaky behavior as the lack of the exploration over the physical path, so which then converges towards a single path rapidly. And therefore, ENCTC tries to enforce such exploration by utilizing the maximum entropy regularization. In details, ENCTC adds a regularization term which maximizes the entropy over the path given input and output sequence. And therefore, ENCTC loss function looks like this form. So while decreasing the CTC loss, the ENCTC tries to maximize the entropy over the path, which means that the model should explore over the visible passes. So from this figure, we can observe that compared to the non-blank symbol prediction from CTC, which is very peaky, and also misaligned with the image, ENCTC predictions are less peaky and also shows reasonable alignment with the original image. However, such ENCTC also has a critical limitation, and we will discuss that limitation and introduce a adaptive maximum entropy regularization. The main limitation of ENCTC is that the use of fixed weight for entropy regularization. Due to its fixed weight, ENCTC constantly enforces the entropy in its prediction. So during the initial stage, everything is still uncertain, so it is indeed important to encourage the exploration over the possible passes. However, after some training, model has then clear understanding of what is correct and wrong, and it is important to focus on the correct prediction rather than keep exploring. However, ENCTC's fixed weighting causes the entropy to keep increase in this figure, like in this figure. So this causes the unfavorable uncertainty in predictions, which can possibly make some room for wrong predictions. Therefore, we propose an entropy regularization which can adapt its weight dynamically. We introduce the adaptive maximum entropy regularization, aka ADAMR. This is our overall framework. The key point is the regularization weight tau in here is a gradient-based variable parameter. In other words, tau is updated during backpropagation with model parameter theta. ADAMR loss is composed of two parts, theta loss and tau loss. We will explain them one by one. Loss for updating model parameter theta is same as ENCTC, but the weight is a learnable parameter tau rather than the fixed hyperparameter. This loss aims to decrease CTC loss while increasing the entropy based on ASR system's prediction. This loss is used only for theta update, so we utilize the stop gradient function to avoid the loss gradient to flow through the tau. In torch, this will be the detach function. Loss for updating tau uses target entropy as a hyperparameter. the target entropy is the desired minimum value of the class entropy. So this loss decreases tau proportionally to the gap between the current entropy and the target entropy. For example, if current entropy is very high, tau will decrease proportionally to the gap between the gap and weaken the entropy maximization strength. When the current entropy becomes similar enough to the target entropy, then the whole loss will be similar to the ENCTC because the tau loss will be close to zero. And due to the entropy maximizing property of the ENCTC, the entropy will increase slightly, and then that slight gap will decrease the tau. As a result, tau will exhibit a very gradual reduction towards zero. If current entropy is lower than the target entropy, this loss will increase the tau to increase the current entropy higher than the target entropy. So this loss is used only for tau of these, so we also use dot gradient function in this target entropy minus the current entropy minus target entropy here. Let's look at the framework once again. First, ASR system theta will predict the softness probability for each time step for each symbol from the acoustic feature inputs. Using the CTC dynamic programming algorithm, we can then compute the conditional likelihood and path entropy. Total ADM loss is then computed based on the learnable parameter tau and hyperparameter target entropy. The theta loss part gradient only use the theta loss part only is used for the theta propagation, and tau loss gradients are only used for tau update. The hyperparameters for ADAM are initial temperature value and the target entropy. For target entropy, we found that using the value proportional to the target length empirically gives good performance. So we performed the experiments on two tasks, which is ASR and OCR. So first, for ASR experiment, we use the deliberate speech corpus, which is a public domain audiobook narrations, and which is used for not only speech recognition, but also various tests for the speech domain. We use the training set, which has 960 hours of utterance, and we evaluated on test clean and test other for clean and noisy speech recognition. We use two kinds of models, which are RNN-based and transformer-based. For RNN-based model, we employ the bidirectional ISTN encoder with CDC. And for transformer-based, we employ the conformer, which combines the convolutional module between the transformer architecture which captures the both local and global dependencies in speech. In details, we use conformer small encoder and use CTC instead of the transducer decoder, which was used in the original conformer paper. These are the results of the ASR. So compared to the CTC baseline, we can observe that the ADAM or performance gain is higher than the ENCTC for all cases. These are the framework predictions for each loss. Colored lines indicate the non-blank predictions, and gray dotted lines indicate the blank predictions. First of all, we can observe that the peaky behavior in CTC, where it is full of blank symbols, and almost every non-blank prediction only takes single frames. On the other hand, ENCTC and ADAM predictions show more wider patterns, which also provides more reasonable alignment compared to the original data. The difference between the ENCTC and ADAM comes from the confidence of the correct prediction. For example, in here, the prediction for token D in time step 92 for ENCTC shows lower confidence even though it is the correct prediction. On the other hand, ADAM shows both wider pattern with higher confidence for correct predictions. This shows that while ENCTC allows unnecessary rooms for incorrect or blank prediction due to its constant entropy enforcing nature, ADAM can balance between ambiguity and certainty through its dynamic regularization. Next, we show the OCR experiment. Data used for training is MJ6 versus the large-scale synthetic text recognition dataset. And for evaluation, we use 3 real-world text recognition datasets, benchmark datasets. We also adopt the RNN-based and transformer-based model for OCR. For RNN-based, we use CRNN, which is one of the widely used OCR models. CRNN extracts the visual feature using the convolutional layer and outputs the frame-wise prediction from this visual feature sequence using the bidirectional LSTM.
연결은 줄 거예요.
응?
그 연결 지금 So what's the connection? 다시 나오고 있어요.
Yeah. So, we also adopt the RNN-based and transform-based model for OCR. So for RNN-based, we use the CRNN, which is one of the widely used OCR models. The CRNN extracts the visual feature using convolutional layers and outputs the frame-wise prediction from this visual feature sequence using the bidirectional LSTM. And for transform-based, we employ SVTR, which is a single-step visual transformer for OCR. In detail, SVTR divides the images into patches and aims to map each path to the character components. Therefore, we can train the prediction for each patch with CTC. So these are the results for OCR. We can observe higher performance improvement of ADAMR compared to ENCTC for both models and all benchmark datasets. Let's look at the frame-wise predictions. CDC, in this case also, CDC shows peaky distribution for OCR. And also predictions such as T and S shows poor alignment of the CTC. On the other hand, ENCTC and ADAMR shows wider pattern and also more reasonable alignment. The difference of ENCTC and ADAMR can be seen in this age prediction. In ENCTC, the prediction for age is not only low but also has high prediction for N, which is a wrong prediction. On the other hand, ADAMR shows wider pattern with high confidence for correct predictions. And this shows that ENCTC constant entropy forcing make a room for incorrect predictions, while ADAMR balance the ambiguity and certainty. Now let's see how tau and entropy evolves through training. As you can see, entropy in ENCTC first drops drastically and then constantly increase throughout the training process. On the other hand, ADAMR maintains the entropy to certain value, which is our desired minimum value with target entropy. Also for tau, we can see that the decreasing rate of tau drastically decreases when the current entropy reaches the target entropy. This shows that the ADAMR functions properly as we intended. Next, we explore the effect of the hyperparameters. As seen here, initial temperature tau do not affect the performance significantly, since ADAMR can adapt its temperature according to its training procedure. You can see that regardless of the initial value, tau becomes similar in the later stage, in this here. This shows the adaptive nature of ADAMR temperature. On the other hand, target entropy affects the performance of the ADAMR. In details, if the target entropy is too low, it might not be strong enough to mitigate the CDC entropy minimization. On the other hand, if target entropy is too high, entropy regularization might be too strong and then forcing excessive uncertainty, hindering the correct prediction. Optimal target entropy depends on the model and data set, and choosing the appropriate target entropy is very important. To summarize, CTC suffers from peaky behavior and overconfidence, and we propose ADAMR which can balance between ambiguity and certainty by adjusting the strengths of the entropy regularization. And our experiments show that ADAMR functions as we intended and ultimately improves the performance of the CDC-based ASR and OCR models. Thank you for listening.
Okay, thank you for listening. And we have any questions. what I want to ask you is the second question. Is there any specific formula in computing the probability in the CTC procedure?
CTC, so your question is that is there any formula for so you're asking is there any specific formula to compute the what is it? Compute
Oh yeah.
what?
좀 뒤로.
어디?
뭐지? 예. 아까 그 슬라이드에서 그거 확률을 계산하시는 것 같은데 혹시 제가 잘못 이해하고 있는 건지.
네, 확률 계산하는 거 맞아요.
지금 여기서 그걸 계산하는 혹시 아까 앞에 있던 그 공식.
네, 이게 CTC가 계산을 하는 것들이고요.
What does L and pi represent?
L is the target sequence. So CTC is trying to maximize the conditional likelihood, the target sequence or label sequence, even the input sequence. And pi is the alignment. So the conditional likelihood is the sum of the every possible passes of the given input. What's your question? Yeah.
That was it. And another question?
Is there any questions? 소리가 나오고 있는 거예요?
네, 잘 나오고 있어요.
네, 그러니까 지금 사람들 소리가 나오는 거예요. Is there any questions? I didn't hear. If there's no question, then we end here for.
Okay, thank you for your introduction and your defense theme, and let's give a big applause. Thank you. And sorry for the disconnection due to the unstable internet. Thank you.